And welcome to lesson 32 of my DP chemistry series. This is structure 3.1.7, discontinuities and ionization energy, HL. This is very much a review of structure 1.3.6, where we talked about trends in ionization energies. Today we'll be further discussing the trend of increasing ionization energy with the two discontinuities and how they evidence existence of energy sublevels. So, explanation should be based on the energy of the electron removed. So we're going to specifically looking at the electron removal and not really talk about specific stability of orbitals. So with that said, let's just go ahead and talk about those two discontinuities that we saw in ionization energy. And then you know what? Instead of a graph, we'll just use an image that we already have for ionization energy. So in this graph, we already noticed that we have this discontinuity here, here, and here. And we notice that between beryllium and boron, that ionization energy jump is very similar to magnesium and aluminum, being between group 2 and 13. Meanwhile, nitrogen and oxygen and phosphorus and sulfur are very similar, being between groups 15 and 16. So we already learned a little bit about that, but let's evaluate it with a bit more depth. So let's talk about discontinuity 1. Discontinuity 1 is going to be the one between beryllium and boron, as well as magnesium and aluminum. So as we talk about them, we're just going to look specifically at beryllium and boron, but it works the same both ways. So we're going to draw two energy level diagrams with the 1s and 2s orbitals. Now, this is for beryllium, and for boron, we have our 1s, our 2s, but we also have our 2p. Now, these are fully filled s orbitals, but boron has one electron in the first 2p sublevel. As we look at the ionization energy, to remove an electron from here, it's about 900 kilojoules per mole. Well, this electron right here is about 800 kilojoules per mole. And that discontinuity specifically comes because the p sublevels are slightly higher in energy than S of the same N. So N equals 2, 3, 4, whatever, etc. It doesn't really matter. But of that energy level, we have that change. So this is energy, and this is energy. So that shows us that we have a weaker attraction between this level. Therefore, this weaker attraction between nucleus and valence electron provides the evidence, specifically like what we had, of existing energy sublevels. Existing energy sublevels, such as the P sublevel that we are looking at here. So that shows us that type of discontinuity and explains it in terms of energy. Our second discontinuity, discontinuity 2, is between nitrogen and oxygen, as well as phosphorus and sulfur. So for discontinuity 2, we may remember, and I think I'll be a little neater here, energy, and we have our first box, our second box. Yeah, maybe I should have just done this from the start. And our third box. So in this case, we're going to be looking at nitrogen and oxygen. It's just easier because I have to draw fewer boxes. And we fill in our s orbitals as they are all fully filled s orbitals. And nitrogen has one electron in each of the 2p, while oxygen doubles up in the first 2p orbital. When we're looking at the removal of these outermost electrons, nitrogen comes in at about 1400 kilojoules mole inverse, while oxygen comes in at about 1300 kilojoules mole inverse. So these are values that we get for ionization energy of these electrons. So we can explain it by talking about this double occupancy here. The double occupancy of the 2p orbital in oxygen provides extra repulsion between valence electrons. Therefore, this is going to reduce the overall net attraction from the nucleus. Therefore, we're going to have that greater repulsion and thus an easier ionization energy or smaller ionization energy for this electron. So this is very much similar to what we covered in structure 1.1.3, but we're just adding a little more depth and a little more detail. And we're going to be talking about it with numbers, ionization energy specifically, and that attraction from the valence electron to the nucleus. So I hope this helps and have a great day.